Students, now we shall discuss the topic open sets. So topic is open sets, and this is coming under unit number 5. The section is 5.4. So we are going to discuss the topic is open sets. Now first we will define what is an open set. Already we discussed what is an open ball generally in metric space. Now we are going to discuss what is an open set. There's a difference between open ball and open sets. We are going to define open sets in terms of open balls. Now the formal definition. The topic is open sets. Now what is the definition? The definition of open set. It's a very important one. So now we are going to deal completely in metric spaces. Let us consider a metric space. Let M be a metric space. Let M be a metric space. We say that the subset say G of M. You can write like this also. The subset G of M. Like this also we can write. The subset G of M is an open set. When we call the set G is an open set of M, if for every element in G, there exists a real number, or that is greater than 0, such that real number or greater than 0 such that the entire open ball B, whose center is X and radius is R, is completely contained inside G. If this happens for every element of the set G, then we say that G is an open set. For example, you take, this is a metric space under consideration, for example, and this is a metric space with metric row, and suppose I say this is G. This is the set G. I say that G is open. What is that definition says is, you take any element. Suppose I take one element, say X. Suppose I take a single element. I am taking an element, say X. Then I can find many open balls about X. The radius if increase, I can find many open balls. That open balls may go outside this set also, but there exists at least one open ball whose center is that X but radius is R, which is completely inside this G. If this is true for every element, say X, next element is Y, etc. If this is true for every element of the set G, this property is satisfied, then that set G is called as an open set. Suppose this is what? G. I take one arbitrary element, a general element, say X. Suppose I say this element is X. So what should be the case is, about this element, there should be at least one open ball. Suppose this is X. There should be at least one open ball about this element X. Center is X, radius should be what? Some other real number or greater than 0. This open ball should completely inside what? This set. This should be satisfied for any element you take. Suppose I take another element, there must be one open ball with center with that completely lying inside G. This is true for every element of G. Then if this is satisfied, this condition is satisfied, then as per the definition we say that G is an open set. Now we will see some examples. Suppose you take one ellipse. Suppose you take one ellipse, something like this. So, set of all points in the plane inside an ellipse, inside the ellipse, except the boundary. You take all points inside the ellipse. Suppose you take one point P inside this ellipse. P. We can draw a circle with center at P and radius is such that this is completely inside what? This ellipse. So the set B of points inside the circle is an open ball. So this is an open ball. So like this, any point I take inside the shaded region, I can find one open ball with center at that point completely inside the inside of an ellipse. So the shaded portion, that is the inside of an ellipse, is an open set. This is just we are by intuition. We are not making a deep analysis. By intuition, by seeing it, I can say that this set is open. Now we are going to see what is about a general metric space. Now the important result we are going to prove is, there are many examples we are going to discuss. This is just we are seeing it, we are visualizing it, and we try to understand it. Now the important result we are going to prove now is, just write like a theorem so that we can put a continuous numbering. So far we have discussed two main definitions. First we discussed what is open ball. What is an open ball? And using that we framed first is open ball. Using this definition we defined what is an open set. An open ball is like this. It is set of all elements X such that the distance between X and that center must be less than the radius. This is a set, and in general this X element of a metric space, not only real numbers. So this is an open ball. Using this definition, just now we proved what is an just stated what is an open set. Now we are going to show one result is, what about open ball? So now we are going to see that every open ball is itself is an open set. Prove that every open ball is an open set. Every open ball is an open set. Let us consider an arbitrary metric space. Let M, rho be an arbitrary metric space. Let M, rho be an arbitrary. Now let M, rho be an arbitrary metric space. We just take arbitrary metric space. If we prove this result, then it is true for any metric space. That's why we always use the word arbitrary. Arbitrary metric space. Let us consider an open ball. So suppose I take one metric space as M, rho. So now we are going to show that every open ball itself is an open set. So now we are going to take one open ball, say B. I name this as something like script B. That is nothing but the open ball whose center is A and radius is S. Center is A and radius is S. So now this is an open ball. Now we are going to show that this open ball itself is an open set. So what we are going to do is we will take one element inside this open ball. We will prove that there exists another open ball which is inside this open ball. So then this is true for every element inside this open ball. Therefore, as per the definition of open set, this open ball is an open set. So this is what we are going to do it. Let m comma rho be an arbitrary metric space. Let us consider a open ball say I'll give the symbol like B. That is nothing but center is A, radius is S. Something like this. We are considering this open ball. So now we have to prove that this open ball is an open set. Now we shall prove that this B is an open set. So what is the definition of open set? We are going to take one general element inside this B. This is B. And we are going to find another open ball whose center is at X but completely lying inside like this. If we are able to find this one, this is true for every element inside this open ball. Therefore, as per the definition of open sets, the script B, this one, is an open set. We are going to define let T equals to the distance between X and A. See, we are going to take one element X in. Let X is an arbitrary element in this open ball. I am going to take one general element, say X. So now, since it is inside what? This open ball, which is B, whose radius is what? S and center is A. So now I am going to define the T is nothing but the distance between A and X. That is by T. And let R be any positive number such that positive number less than S minus T. And very important thing here is where S minus 3 is greater than 0. Why S minus T is greater than 0? You see here, this is the radius of this open ball. This radius is S and this element is inside this open ball. Therefore, the distance between this see, I will just draw this one a little bit bigger so that you can understand. A little bit bigger. Okay, suppose this is the center of the ray and this is the radius, that is S, and suppose you think that this is my point X. This is a point X and this distance we give it the name what? T, just now. See, the distance between X and A is T and this total length is what? S, that is radius of the bigger the ball, open ball. So what would be the difference between S and T? Should be definitely greater than 0 because S is bigger than the distance T, it should be. Okay, so T cannot be greater than S. That you can clearly see from this diagram. So that is why S minus T is positive. So we have to choose that let R be any positive real number such that it is less than this S minus T, which is a positive number. Now what we are going to do is, this is what open ball we are going to consider. So now I am going to construct an open ball like this, whose center is at X and radius is what? R. We are going to show that this open ball is inside this open ball. That's what is finally we are going to claim. So let R be any positive number such that it is less than S minus T. Now let now if suppose there exists an element Y which is element of this open ball B of X colon R, suppose I take one element inside this set, inside this Y is element of X colon R, then what happens? Then now we are going to check the distance between A and Y. What's the distance between A and Y? As per the triangular inequality, this is less than or equal to rho of A comma the third element plus rho of X comma Y. But what is rho of A comma X? This is equals to T, and rho of X comma Y should be less than R. Why it should be less than R? Because I take an element Y inside this this one, this open ball, whose radius is R and center is X. So distance between X and Y must be less than R. So what happens is, overall this is less than T minus T plus R. And what about R? Already we have assumed that R is less than S minus T. This R is less than, in place of this I am going to substitute S minus T. So what happens is, this is what? That is, the distance between A and Y is less than S. So what happens is, if distance between A and Y is less than S, then this Y belongs to what? Then this Y belongs to the open ball B of A colon S. This is nothing but this one, the bigger one. So what we have proved is, we have proved that this script B is an open set. How we prove this is an open set? Say for example, again I am just drawing this. This is a metric space under consideration, and suppose this is an open ball, say B, whose center is what? A, and radius is S. So now we have to prove that this open ball itself isn't, this open ball is nothing but B of center is this and radius is S. This open ball itself is an open set. For that we are going to take one more element here, and we are going to show that there exists an open ball around this general element we took from this, such that this is completely inside what? This B itself. So this is an open ball which is lying completely inside B. For that purpose, see, we took one general element in B, say X. We took one general element in B, and we tried to prove that there exists at least one open ball whose center is X, like this, which is completely inside B. So for that purpose, we take an open ball like this one, and we take one general element in that set. If I show that this Y belongs to what? The bigger set B, then what happens? This open ball belongs to this B, because already we discussed it many times. If we want to prove that A is a subset of B, what we do is, we take one element in A then try to prove that this element belongs to B. This is what we have done. So we took one general element from this small open ball whose center is X, and we finally proved that that open ball, that element belongs to the bigger set. So what happens? This entire open ball, this one, is inside this B. So that's what I'm going to write next time, which implies B of X colon R is completely inside this B. And since X is an arbitrary element, every element of set B satisfies this property. So which implies that this satisfies the definition of open set. This implies that B, which is nothing but the open ball, center at A and radius S, is an open set. So that's why we take one R, any positive number that's such that it is less than S minus T. Like this we take. Otherwise it will go that open ball may be going outside that capital B. So that's why we take, it should be less than like this element is possible. So now I take one general element in that this one, and we are going to check what is the distance between A and Y. So that is using the trigon equality, and A and X is, I assume that it is T, and the distance between X and Y we assume that it is less than 1, S minus T. So finally what happens, this get cancelled, it is equals to S. So distance between A and Y is less than S. So what you can tell, this Y belongs to the ball, this open ball. Okay, so we took one general element of this open ball, finally it is inside this kept B. So what you can tell, this entire open ball is a subset of this open ball, and this is true for a general element X. So like this, everything, every element in this B will be satisfying this property, and hence B is an open set.